Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the University of Helsinki, where I study cool things happening inside the universe. So I'm a cosmologist, so that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, all of the cool stuff happening inside the universe. And I love chatting about all the fun things in the universe and answering any questions people have. So most weeks I'm here on HAPS, on Cup of Cosmology, chatting to everybody. HAPS, Twitter, Twitch, YouTube, we're out to all the platforms today. And you're welcome to come in and ask questions. And today, rather than me rambling by myself, I do have a guest with me, so I'm going to bring Chris up on screen. Hey David, great to see you in first. Very nice to see you in the comments here. So we should be seeing Chris on screen now. Let's see. Hey Chris, welcome to Cup of Cosmology.
Hi Deanna, how you doing?
I am doing well, enjoying the weekend. It's been a fun weekend. How are you doing?
I'm doing great. Yeah, it's super sunny here in the UK, so I'm enjoying that as well.
Nice, nice. It's actually snowing here again in
No
Helsinki.
way, no way. Apparently we might have snow next week, but it's really sunny right now.
Nice, nice. Make the most of it before the snow comes. Just want to say hello to Scott in the comments and Paul. Great to see you. And David, thank you so much for the Love Burst Award. I do appreciate all of the awards. So, Chris, do you want to introduce yourself to everyone?
Yeah. Hi. My name's Chris Patterson. I'm a postdoc. Well, I'm something called an innovation postdoc at the University of Portsmouth, which is on the south coast of the UK. I finished my PhD a couple years ago, and I studied the very early universe during my PhD, and now like I say, do something called innovation, which is taking techniques in astronomy and using them to study other areas of physics. So it's a very different thing to what I did in my PhD, but it is a lot of fun, and it's a challenge, but it's super cool, I think.
Yeah, I just want to say hello to Anne's joining as well. And I know that the HAPS notifications are still not working properly, but hopefully if you're following me on enough platforms, you should get the notifications anyway. So, yeah, I've actually never heard of an innovation postdoc before. So, how is that different from a normal postdoc, other than that you branch out? Like, how is it different to a normal postdoc?
In day-to-day activities, it's not super different. It's basically just, I think it's just where the funding comes from. It's from an agency that supports interdisciplinary collaboration and work. So rather than carrying on studying the very early universe, I just take the tools and techniques from astronomy and just try and apply them to other areas.
Nice, that's very cool. So, I guess you work not just with cosmologists, but from people of all different fields as well.
Yeah, that's right. And to be honest, that was one of the biggest learning curves, is learning to speak to people that aren't cosmologists about research and about the tools from cosmology. So, for example, I collaborate with lots of like actual medical doctors rather than doctors of space, which is what I'm used to. And it's just the language that you have to use is totally different, and the way they think is totally different. So that's really interesting, but also it was a challenge at the beginning.
Yeah, I can imagine because we're used to speaking to people who understand the jargon of cosmology when we're doing actual research. And of course, when we do outreach, we're more careful with the jargon. But speaking on that level of trying to actually do research without using all of your jargon words is definitely sounds like a challenge, something that takes a while getting used to, I can imagine.
Yeah, it definitely does. But it also works the other way, because when they're using like medical jargon at me, or using, all sorts of these names of different drugs and things like that we talk about, I have no idea what's going on, and frequently have to be the kid in the corner that's like, sorry, I don't know what that means. Could you please explain that?
Yeah, but it is always important to ask questions. And I think sometimes, even if you're the one asking, it's likely that other people in the room also have the same questions. So it is always important to ask questions.
Oh, for
Let me
sure.
just remind everybody watching here that this is an interactive stream. So I see you all chatting on yourself. That's great. Do feel free to ask any questions. We're going to try to answer any questions you have for us. And if you don't have questions, I get to ask all the questions, which is also fun. And I do see someone in the comments saying that we're on the day where we pretend the Earth's rotation is 23 hours. Yes, I hate daylight saving time. I've ranted about it multiple times. Let's see how long I can go without ranting about it today. Comment from Paul: my daughter is choosing college and leaning towards a school that is pushing their interdisciplinary program. That's great, Paul. I mean, I think interdisciplinary programs are definitely the way to go. And I'm sure you agree with that, Chris, given that that's what you're doing as well.
Yeah, absolutely. It also helps me answer the question when people used to ask a lot during my PhD, why study the early universe? And beyond, because it's fun and because it's
Because we
interesting
can.
because we can, it's super cool to understand where we came from in terms of the universe's evolution. But now I can say, and also I can give you these examples of how the tools we develop doing this like theoretical or observational cosmology actually do apply to other areas and how they are useful and how they push research in other areas forward too, in perhaps more like everyday situations.
That's really interesting because it is a question we get often of like, why do you bother studying these abstract things? And it's always the answer of like, just the scientific knowledge will be useful at some point. So before we get into what you're doing now, maybe you can just tell us, because you said you studied the early universe, and I've had a few guests on recently who are studying phase transitions. So what you're studying would be even earlier, or what you did study during your PhD is even before that. So do you want to tell us a bit about what you did during your PhD?
Yeah, sure. So I studied a period of time called inflation, which is, in my opinion, basically the earliest thing you can study in a meaningful way at the moment. Um, it started sort of, a fraction of a fraction of a fraction of a second after the Big Bang. It lasted an equally short amount of time and it ended. And it basically, during that time, the universe went from being, or the observable universe that we live in now, went from being a subatomic speck of space to a much bigger but still very small, sort of this size volume of space. And loads of interesting things can happen during inflation. And in particular, I was looking at how quantum mechanics and the universe, how it behaves during inflation, can impact things later on, like black hole formation after inflation ends. Which I guess phase transitions can come into a little bit, but I was very much focused on the inflation part, and then the other bit was sort of, and then black holes might form, without worrying about the technical details of that.
I think inflation is always a cool topic, and people here on the show have heard me talk about inflation a few times, at least the regulars. Hello to anybody new, by the way. There's always the question of how can you actually try to study inflation, given that we're talking about something that was 13.82 billion years ago, lasted a fraction of a second. How do we study this?
Yeah, it is super hard, and lots of it is theoretical, but there are sort of things in the universe now that can only be that way because of what happened in that fraction of a second after the Big Bang. I know, Deanna, you're a huge fan of the CMB, but that
Obviously.
is one of the most powerful observational tools we have to justify inflation. Basically, it's an incredibly uniform surface of light that we can see in the universe, and explaining that without inflation, like why it's so uniform, you either have to just say the universe has been uniform forever and that's why, which is not very satisfying, or you can justify it with inflation, which is a much more satisfying thing to do, I think.
Yeah, I do like that we can use the CMB to talk about inflation. And thank you for giving me the chance to bring up the image. There's an ongoing joke with my fans that I cannot spend the whole stream without showing it, and we lasted like 8 minutes before the CMB appeared today. So
Yeah,
you gave me the chance nice and early.
I used to think the CMB was like a cool thing that was out there, but I, wasn't that interested in it. And then the more, like, this is when I was like an undergrad, I mean, and the more I learn about cosmology and observational cosmology and even inflation, the more you realize the CMB is like the most important thing probably in cosmology, I would say. It comes up all the time. Anytime like dark matter, CMB comes up. Inflation, CMB comes up. Dark energy, CMB sometimes comes up. And
I
it's super
promise I
cool.
did not invite Chris to the show just to do a sales picture of the CMB.
No, but like I say, I used to just be like, it's cool, but it's not my area. And then I realized it's everyone's area.
It's everywhere. It's like so many things hidden in the CMB. I just want to say hello to Rohit Paul joining from YouTube. I do believe that's on your YouTube account. So your YouTube account successfully connected. So that's good to know.
Awesome. Yeah, I've never done this before, but it seems to be working, which is great.
Yeah. It showed me that we were going out to your YouTube as well. So that should be all set. We do have an interesting question from James here when we're talking about inflation. I thought inflation was still continuing. So what is the difference between inflation and the current expansion of the universe?
That's a that's a super good question.
It's a big question.
It's a big question, and it almost comes down to your philosophy actually at some point, because different cosmologists think different things about this. But if we just talk about our observable universe, then inflation is like right after the Big Bang, it got the expansion accelerated exponentially, which means it kept getting faster and faster and faster and faster and faster, ad hoc. And it was sort of this explosive expansion that happened very quickly. And then it ended, and it carried on expanding just at a much slower rate. And it did that for the universe expanded at this slower rate for a very long time. So in this picture that Deanna's just brought up, inflation is the sort of when it gets really, really wide, really quickly, right at the left-hand side, and then you can see that the expansion since is much more gradual and slow. So it is still expanding. It's just the speed at which and how quickly it's accelerating that's different. And then dark energy is something that's starting to dominate the universe now, and this is something that we also think is accelerating the expansion in an exponential way, probably. But is probably different to inflation, but there's lots of ongoing discussion about that.
Yeah, there's a lot of discussion whether basically the expansion now is like a second wave of the initial expansion that we had. It's quite hard to disentangle these two, other than one was in the very early universe, one is later on today. But otherwise, they're concepts that are very, very closely related. And I see the Reddit connection is working as well. So hello to everybody watching on Reddit. Great to see you as well. David Dunn, astronomy professor in the audience here, is asking, how does eternal inflation fit into this picture?
Yeah.
All the tough questions today.
Eternal inflation is, I feel it's super interesting sometimes, and then other days I feel a bit jaded about it because it's so hard to study it or in a meaningful way, I think. But eternal inflation is sort of, inflation carries on in the universe all the time, and little bubbles stop inflating, and like a little bubble that stops inflating would be our observable universe, and then other universes, like little observable bubbles, would pop out in different places that we could never talk to because inflation between these patches carries on. So we're flying away from the other bubbles at an incredible speed. But again, it's hard to test that experimentally. It's really theoretical. But that's what eternal inflation is. That sort of the default of the overall universe is inflation, and we're the weird patch that stopped.
Yeah, it's very interesting to think about these different bubbles. And if anyone was tuning in the last few weeks, we were talking about bubbles or new phase. And you can think of it something similar, where you would have these patches of bubbles with the difference that these could actually never come into contact. And we do want to move on from inflation at some point, but people have a lot of questions about inflation. So we're getting a question in from Reddit of, does the inflation cause the speed of light, or does the speed of light already exist as a constant? I think it's quite difficult to relate the speed of light to inflation because they're very different concepts, right? So we have the idea that nothing in the universe can travel faster than light in a vacuum, and this is something that you can see with electromagnetism, you can see it in general relativity. I'm not sure how we would connect that, if in any way, to inflation.
I think that's a really, really difficult question to answer because I guess the return question I would pose is, did light even exist during inflation? Because like it's sort of the universe was just sort of a soup of energy, and it's hard to know whether light in the way we know it even was a meaningful concept then, because maybe the standard model almost certainly hadn't formed in the way we see it now. So I would say there's some sort of causality limit very similar to the speed of light, but it's a really interesting question that I definitely don't know the answer to.
It's definitely a complicated question. I love when people have questions here that just stump us, because then it's like, I'm going to go think about that.
For sure.
We also have a very interesting question from David Howden watching on HAPS of, does it expand the same way everywhere? And I'm not sure if you mean during inflation or today, but let me address the question of today, because it's a really cool topic and we think so. But also we have issues that depending how we measure the expansion rate of the universe, we get different answers, which is kind of a problem. So one idea here is that maybe there's different regions of the universe that expand at slightly different rates. The thing is, you can get an expansion rate again from the CMB, and this is kind of the expansion rate all over and not in one specific place. But we do think that it's expanding at the same rate everywhere today. Would you say the same is true during inflation?
Yeah, I think, as you know, again, that's a really great question. But I think as far as most theories go, yes, it would have been the same everywhere. But I think one of the reasons that's such an interesting question is And one of the issues I have with the universe is that we only have one observable universe. So
It's a
it's super
problem.
hard to, it is a problem. It's really hard to compare that. Like, we can't compare our observable universe with a different patch of someone else's observable universe because we've only got one. So it's hard. We're doing statistics on one data point at that point, which is, notoriously difficult.
Yeah, I think if you ask most cosmologists, like, what would the best gift be? It's like a second universe, please. Just it would make things so much easier.
And some way to talk to it as well.
Yes, definitely. It's not helpful if it's just somewhere out there in the multiverse. I see the sad bat on Reddit. You're asking questions about white holes and gravity. Those are very fun topics, but I do want to try to stay a bit on topic today. So very quickly, gravity is a curvature of space-time. It's also a force. It tells objects how to move. White holes are way, way beyond what we're going to discuss today, I think. Unless you want to discuss white holes, Chris. If it's like a pet project you want to jump into. Otherwise, we can carry on with inflation.
No, we can say a word about it.
Go
I
ahead, all
actually
yours.
part of my master's project before I was doing my PhD was on black holes, and often when you study black holes, the topic of white holes come up, and white holes are kind of just the opposite of a black hole in some sense, in that black holes are a region of space that gravity is so strong that nothing can get out of that region, and hence you see sort of almost like a hole punch in space. There's this black region that you can never see anything out of. Like, if you fall into a black hole, your future becomes inwards. It, like, space and time do this cool thing where they kind of swap roles, and rather than your future being a place in time, it's a place in space, and it's the center of the black hole. For a white hole, we've never seen a white hole. We don't even know if they actually can exist. But theoretically, what they would be is the opposite, in that if you're inside a white hole, your future is out. It's impossible to stay inside a white hole. It's a region where things would just stream out of it. And I guess they're called white holes because a lot of light would probably come out of that, and they would be very, very bright, the opposite of a black hole. But
Yeah.
I don't know much more technical details than that, I'm afraid.
No, I think that's a very nice answer to the question, of like a very nice introduction to white holes. Scott is pointing out that the universe itself does sound a lot like a white hole, and that is an interesting question, and you can draw some parallels there.
Yeah, was the beginning of the universe a white hole? That's a good YouTube video title, I think.
Yeah, definitely. That's something that I think requires a bit more preparation than just jumping into questions live.
For sure.
Thank you, David Howden, for the Love Burst Award. I do appreciate all of the awards you all send me. Very much appreciated, always. Following on the topic of gravity and white holes, we have the question of where does gravity come from and what causes it? Tough question.
Very tough question. It took Einstein a long time to figure that out.
So, all yours if you want to answer that one.
Sure. So our leading theory of gravity is that it's a bit different to the other forces we know where they're carried by some particle, but rather heavy things in space just warp space-time, and therefore gravity is just things following this warped path towards a heavy object. And that's, for example, you can picture, I know the classic example, which has its pros and cons, but is like putting a heavy ball on a trampoline, and that's like something heavy warping space, and then other things fall towards it just because they're following the shape of space rather than any sort of interaction, like a particle-based interaction. So it's kind of simpler than the other forces in that sense, in that it's just heavy things warp space in a way that makes other things fall towards them, kind of like that trampoline analogy.
Yeah. So we actually understand gravity a bit better than some of the other forces, but still we have the issue that gravity, we're not completely sure how it fits together with everything else and how it fits together with particles and like how do particles feel gravity. We're still working on that, but as Chris was saying, the idea is gravity is just a curvature of space-time. So there's the way of like paraphrasing Einstein's general relativity, which is objects with mass tell space-time how to curve and space-time tells objects how to move. So something massive will curve space-time. This produces a gravitational effect. This makes other objects follow the gravitational effects. But I think we could spend a lot of time talking about gravity, and I will just take this chance to mention that next week's topic is actually going to be general relativity. So perfect. I have a professor from my department joining, and I asked what topic we're doing, and I think we agreed on general relativity. So that's going to be fun. So all of the gravity questions for next week.
Very good. So I can defer to someone much more knowledgeable than me next week.
Yeah, just pass it on. Just if it out.
Ask again next week, everyone. That's how it'll be.
Yeah. That is my default answer if I don't know a question. Like, oh look, look that up. Ask me again next week, and then sometimes people forget, and then I don't have to look it up. We do have an interesting question from Paul, which is moving away from inflation, but I think we answered all of the main inflation questions for now. Can software be used on the JWST imagery to compensate for diffraction and other artifacts? And I believe you actually put out a video about this telescope a few days ago on your own YouTube channel, so perhaps you can answer that question if you want to.
No, yeah, I would love to. I've been enjoying talking about the James Webb Space Telescope a lot this week. So I guess maybe some context in that this week, or the end of last week, the James Webb Space Telescope put out a brand new image of a nice bright star to show that it's all of its mirrors, because it launched folded up because it's so big. They had to do a very delicate process of aligning all the mirror segments so that they work as one big telescope rather than as lots of little telescopes being smushed together. And they put out this nice image of a bright star in incredible detail to show that it basically, look, we've done it, it's working as one great telescope. And I think probably the most noticeable feature of the star is, rather than looking like a ball in space, like a big fiery ball like we know stars are, it had sort of 8 diffraction spikes, as they're called, coming out of it. So it looked very spiky and looked maybe more like a sort of gospel story star, like you would draw maybe if you study the Nativity. But it had these 8 spikes, and they're called diffraction spikes, and they're just caused by how light moves through the mirror. There's 8 of them. 6 come from the fact that the Webb telescope mirror is a hexagon, and basically one edge gives you a diffraction spike, so you get 6 from 6 edges. And there's a couple of extra ones that come from the struts that hold up the secondary mirror, and that some of those line up with the ones that already exist, and you get an extra one, so you end up with 8 spikes around the star. And we know exactly why they're there, and it was completely expected that they would be there. And there's kind of nothing you can do. If you just take one image, they're going to be there. But because we understand it so well, there's often the question of, can we just remove them with software? And the answer is yes, but you do lose a bit of resolution and contrast in what you leave behind. So there's almost never a reason to do it unless you're studying the exact sort of point in the middle of the image, and you really want to see that. But otherwise, you end up with sort of like a bit more grainy images, and you lose a lot of resolution. So the answer is yes, you could, but there's almost never a reason to do it. And lots of these images that have them are getting released to the public. And I think NASA and lots of people think they look amazing with these diffraction spikes. Sorry, and so they leave them in because they look awesome. I hope that answers the question.
I think that's a very nice answer to the question. I got distracted trying to find the image to bring it up on the screen, but I don't have it saved, so I wasn't able to bring it up quickly. But I think you explained it enough anyway. So, no one discusses the magnitude of that star. Yeah. It's, do you know the magnitude of the star that they were looking at there? Terry says nearing 20 magnitude. I have no reference, so I could say that, maybe, if you say so.
That sounds about right. I'm sure I've read it a dozen times this week, but I'm afraid I can't remember. But it's a very bright star, and that's why the diffraction spikes are so obvious. Basically, some percentage of the light from the object gets turned into diffraction spikes. So the brighter the star is, or the object is in the first place, the more noticeable these spikes will be. If you actually zoom into the background of that Webb telescope image, you can see little diffraction spikes on some of the background objects, and they're not nearly as noticeable, just because those things are much fainter to begin with. And typically Webb is going to be looking at much fainter things, so the diffraction spikes will be much less impactful than they are in this sort of test image they put out.
Yeah, and again, this is not an image to actually do real science with. It's just the test image, just to show that everything is working.
That's exactly what I was just about to say. Cool. It's just a calibration image. It's not for science.
Yeah, but it does look pretty cool. And the fact that we do have first light. I see we're getting a bunch of questions coming in together. Let's see. We can answer this one quickly. What are our thoughts on Interstellar's black hole depiction? It's really cool. I like it. There's some things about Interstellar that I like, some that I don't. But the way they depict black holes is actually extremely accurate and very nicely done. What do you think of that movie? Do you have any thoughts there?
Yeah, I think it's a gorgeous movie, and it loses me at the bookshelf bit, to be honest.
Exactly.
That's when I start to have problems with it. But the physics of the black holes and the interstellar travel is really accurate and really well done. They had a lot of real scientists doing consultancy work on that movie. I think Kip Thorne was involved. Do you know if that's right? I think
Yeah,
it was
that is
him.
correct. Kip Thorne,
Yeah,
who then won the Nobel Prize for the gravitational waves. Yeah,
yeah.
he was involved in that movie. In terms of the black holes, I actually think they developed a technique to visualize black holes for the film that then they actually turned into a research paper. So it actually helped progress the idea of visualizing black holes as well. So that was pretty cool.
Yeah, and I think at least one of the planets in that movie was sort of the distance it was from the black hole, and all of that was worked out by Kip Thorne, and used to be accurate, not just he wasn't given a planet and a black hole and said what would happen. They said, we want this to happen. Where do we put the planet and the black hole to make that happen? So it's really accurate.
Yeah, it is surprisingly accurate. I just got a bit sidetracked by a question here coming from Reddit. Does the cosmology cult include male? I feel like I'm missing a reference to get that question. So I have no idea how to answer that. We did have a question coming in from YouTube just now. You see, we try to stay on topic here, but there are so many cool questions, we always end up going off on tangents.
No problem.
Question coming in from YouTube. How do we know that the universe is 13.7 billion years old?
That's a great question. Do you have a good answer for that, Deanna?
I have an image. So there's a lot of ways that we can calculate the age of the universe. Some things that we can do is like look at some of the oldest stars we know of, and that gives us a lower bound. Like the universe can't be younger than some of the objects it contains. So that's one way. We can also look at the amount of really basic elements like hydrogen and helium, and that gives us an idea. But another way we can try to figure out the age of the universe is using my favorite thing, the CMB, because if you have a different age of the universe, your CMB map would look different. Now, of course, at this point, you do need to assume a cosmological model. So using the CMB and assuming our standard cosmological model, we can figure out that the universe is 13.7 billion years old. Or 13.82 billion years old is the current number, which is pretty cool. So yeah, there's quite a few different ways we can do that, but as always, we go back to the CMB.
Yeah, I'm glad you threw up the CMB again. It's always useful.
It's always useful. It's why it's in the Cup of Cosmology logo now. Like in the logo that I showed at the beginning, I had to have the CMB there as well.
It's a very cool logo, I must say.
Thank you. I was very happy. It was designed by Sania Hiba. I think you also met her at Cosmo, and she designed the logo for me. I was very happy with the logo. And there is just a reminder that there is an Easter egg in the Cup of Cosmology logo that nobody has found yet. It's not the gravitational waves, it's not the CMB. There is an Easter egg in the logo, and nobody has found it yet. So just a reminder to everybody to go find the Easter egg. Got a few more comments on Interstellar here. Okay, longer question here. They can infer the age of the universe by extrapolating the universe back in time when it became close to a point. Yes, basically we can wind the clock backwards and try to get the idea from that.
Yeah, that's a great comment, because it also gets to why you need inflation as well. So I'm a big fan of that, because if you just extrapolate backwards at the speed the universe is currently accelerating at, you don't have time for everything to mix and become a uniform temperature by the time the CMB is released. So you need it to start off smaller than we think, and accelerate quicker for a portion of time. Hence inflation.
Yeah. So again, we do need inflation. I see quite a few more comments coming in. As always, if we miss your comment, I assure you it's not intentionally. We're not deliberately ignoring anybody here. It's just sometimes the comments come in too quickly and we get lost in different topics. So if you feel like we ignored a comment, please know it's not intentionally unless you're trolling us. And then just ask the comment again, ask your question again. We'll try to answer it the second or third time. There is also not a primordial black hole in the Cup of Cosmology logo, but there is an Easter egg and nobody's found it yet. I'm going to keep reminding people until someone finds it. Okay, so we're about half an hour in, and so far we've talked about inflation, which is what you did during your PhD. But since then, you've moved on to other topics. So you mentioned that you're part of this innovation postdoc, and you're working on other things with actual, real, useful doctors, not just scientific doctors. So, what are you working on today?
Today, nothing.
Today, nothing. It's a Sunday. That is a good answer. Exactly. You should not be working on a Sunday. What are you working on currently?
Yeah. So I'm working on two main projects at the moment. The first of which is kind of pandemic related and kind of more general, but it's studying the spread of diseases through droplets, which I think the funding was there because of the pandemic, but it's a very important question anyway. Um, and I guess, is it okay if I just walk you through the basic idea? Because I think it's
Please
super
go
good.
ahead.
So,
I've never worked on this, so I'm happy to learn more about this.
okay, cool. So basically, the idea was bore out of using a piece of software that takes a telescope image and automatically finds all of the bright things in it. So you could, like, rather than doing this by eye or being more accurate than doing by eye, you feed it into an algorithm. It basically circles all of the bright spots in your telescope photo, and then you know all the interesting things to look at. And this I promise this is relevant. So we are now studying the spread of diseases by basically putting fluorescent dye in people's mouths, asking them to cough, turning off the lights, turning on some blue lights so that everything glows, and photographing the room. And then we take those pictures and we run them through the exact same algorithm that finds bright spots in telescope photos. But now we're sort of mapping the droplets from a cough in a room. And so we know exactly how they spread, how far they can go, where they end up. They end up behind people, which is a surprise, and all that things. And now we can actually model the distribution of droplets from like a cough or just someone talking in a room using that same software that we use to study telescope images, which I think is pretty cool. I hope you do too.
Yeah, that does sound really cool, actually. I was just thinking, like, before using the cosmology algorithm, what other techniques do people normally use to find droplets?
Yeah, well, actually, the droplet one is a really difficult one, and there aren't many techniques, which is kind of why we were drawn to this one. But what people often do is get people they lay out, I think they're called agar plates, where you can grow bacteria, and they basically get people to talk or sing or cough into a room over a distribution of plates, and then they just take those plates away and let them grow, and they use that to map the room, so you can see where different bacteria landed. That's a really interesting way of doing it, but it's much slower than the one we have. And I think our one gives you a finer resolution of where the droplets, like how big the droplets are, and where they land. If two land close to each other, they probably grow into one culture on a plate, but we can see them as distinct droplets.
That's really cool, actually. So, how many people are working on this team, on this project? Because I guess you're also working with people who've worked on droplet things before.
Yeah, it's a really diverse team actually. So there's me and a couple other cosmologists, and then we have a few respiratory consultants from the hospitals in Portsmouth, and we have even like some mathematicians, some ophthalmologists, which is an eye doctor, um, some aerosol specialists from Bristol. There's a whole range of people, and it's pretty cool. But like I say, learning to talk to them was a whole different matter.
Yeah, I can imagine with everyone coming from a different background, it must take quite a while to actually find common ground here. So I'm curious, like, how did this project come about? Who had this idea, or were you just like all brainstorming one day and realized?
No, this idea was actually sort of suggested, and then it was suggested, I think, by a couple of the respiratory consultants and the ophthalmologist on our team, and they came up with this idea, but they didn't have well, they had this idea of maybe someone has some technology to do this, but they don't know how. That was their idea basically, and they brought it to the head of our department, I believe, and said, can you do this, or do you know anyone that somehow can work on this? And they said, yes, we can do that, but we'll have to hire someone because no one has time right now. And that's where I came into it. I was the one
Nice.
that was willing to learn how to use this telescope software and modify it to work on droplets. And now we're sort of working through, getting people to cough in different situations, in different places, and comparing them and seeing what the best sort of ventilation for hospitals is, or how much safer outdoors really is than indoors, and really interesting things like that.
Nice. I see that Paul is actually asking exactly what I was about to ask here. So I assume you had to modify the software. How much of it is modified? How much is exactly from the original? Like, how different is the actual software you're using?
The actual bit where it finds the bright spots is exactly the same. It's just how to get photos of bright. So if the fluorescent dye we use glows sort of bright green, and we have to basically turn those images into something that the algorithm can take in. So it's sort of, what I do is I sort of run it through a filter that turns the images anything that's like bright yellow gets turned into white, and everything else gets turned to black. So you end up with images that really look like the night sky because they end up with just sort of white spots on a black background. They look like a star field. Um, and then it's really just getting that data in the right format and in the right structure and cropped in a nice way. So sort of when you take a picture, if you take it at an angle, you get a bit of warping of the image. So things look a slightly different size and shape. And we really want every image to be taken sort of directly down so that things are as true to life as possible. So there's a bit of software we use as well to basically, not all the images are taken like that. So we have this software to de-warp and take into account that, and it can basically, from the angle of the image, it can correct for that warping. So we do that as well beforehand. And then we really do use the software exactly as it is for telescopes. We've played with the parameters to make it as accurate as possible and as effective as possible at finding these droplets. But the actual bit where it finds the bright spots, haven't changed anything.
That is really cool, just to think how you can actually use something that we've been using in astrophysics to just apply it to something like this. There's a very nice question coming in from Reddit, which I think is a very curious question. Would different languages change droplet distribution? Because some languages you might speak more, some are more gargly, is a comment here. So, and some languages are perhaps louder and are more emphatic. Does that change? Is that something you're looking at?
It's not something we're specifically looking at right now, but maybe one or two of our collaborators are looking at that. And as far as I know, without scooping them, the answer is yes, it does change.
That is really cool.
Yeah, so basically the amount of aerosols and small droplets you produce does change based on the language you're speaking. And even like if you're studying people singing, then the type of music they're singing as well really changes. And even things like accents, if you're speaking the same language with different accents, I believe that has an impact on the amount of aerosols and droplets produced as well.
That would be fun. I now want to see a study of like different accents from the UK and see which one produces the most droplets. One could then correlate that to like COVID statistics and see if there's any connection.
See how well it correlates.
Yeah, probably not. We can always find random correlations, but it is very interesting to think about.
Or it will correlate really well in a meaningless way. It'll correlate, but not be, correlation is not causation.
Yeah, correlate, but just happens to be correlated.
Yeah, exactly.
There's a question just going back to inflation that I just want to answer very briefly. So there are two different speeds that we obtain for when we measure the expansion rate of the universe. As Beckenoff is saying here from YouTube, some measurements give you 67 kilometers per second per megaparsec, some give you 74. This is known as the Hubble Tension. It's one of my favorite topics to talk about. And basically, we have different expansion rates of the universe depending how we measure things. One comes from the CMB, one comes from supernovae. I've done a whole stream about that before, so this is just a very short version. Just going to say I'm happy to talk about that another day to stay on topic on these other cool things that I can't talk about, because we should take advantage of having Chris here to learn more about droplets. It's funny because currently when I think about droplets, I'm thinking of like droplets of phase transitions in the early universe, and it's always interesting to see how words can mean very different things in different contexts.
This is one of the things I learned when talking to actual medical doctors. Like
yeah,
the first time I
guess...
talked about a log plot, they had no idea what I was talking about.
Yeah, I guess it's just what we're used to using and dealing with. And I think sometimes it's also very easy to forget just how much of what we say is actual jargon. It's one of the reasons I love doing this outreach, because I say things sometimes and people are like, that's a jargon word. It's like, oh yeah, it's right actually, sorry about that. We just kind of lose track of how much we actually use random words sometimes. Paul has another very interesting question. Does your software use clustering? So if you have a bright spot very near another bright spot, are you able to separate them and tell them apart?
That is a really cool question. And yes, well, it's basically how well it does that is a function of the resolution of the camera used. Basically, as long as there's a couple of pixels between the droplets, yes, it can separate them. Unless they're especially bright, in which case the glow, the flux can sort of leak over, and sometimes it does cluster them, but I do my best to not let that happen. But there's also really interesting correlations, I think, and this is something we haven't studied in great detail, but we're aware of and want to. That often when you have a big droplet land on the floor or on a target or something like that, often there'll be lots of little droplets around it where there's sort of secondary splatter, and that's something we want to study, like how the spin of the droplets can affect secondary splatter around it. So you get a big droplet and lots of small ones around it where it's sort of almost splashed over. But at the moment, we do our best to not group things together that are separate droplets.
And you just said about the splatter and it going outwards. Makes me think that I'm wondering if there's techniques from forensic science where they study blood splatter that you could use to study the pattern of the droplets as well.
Yeah, actually, it kind of goes both ways, because also I think our technique could be applied to blood splatter probably, and see if it's comparable at least to how they do it at the moment, which I don't know in great detail, to be honest, how they do it.
Me neither. I took some courses on forensic science at some point, and we did a basic introduction to blood splatter, and it was super cool, but not to the level where I could actually say anything useful about it, other than we played with fake blood and it was fun. Comment from James here. Are all celestial or cosmological events capable of being studied using all wavelengths? Or is it just a matter of which one is better than the other? It actually very much depends on the object. Like the CMB, for an example, currently is in the microwave range. You can't really use other parts of the electromagnetic spectrum to measure it. Some things will emit in radio waves, some will emit in infrared, some in optical. Some of them will emit in multiple of these, like across a range. And then, depending what you're doing, you can use different probes. But usually, objects emit a different amount of energy, and this corresponds to a different part of the electromagnetic band. So sometimes you can see it in different wavelengths, sometimes you can't. It very much depends on the object you're studying. And don't worry, James, as always, there are no simple questions, there are no stupid questions. All questions are good questions, and we're very happy to answer any question you have. And as always, there is no shame here. You can ask anything you want, anything you've always wondered. This is the place to ask.
Yeah, can I just, like, when I started my PhD, my PhD in cosmology is the first pure physics qualification that I got. So when I started, I had no idea what was happening, and I asked a lot of what people would maybe consider silly questions, but then those questions often get really interesting answers because they're silly, well, not silly, but they're maybe covered at an early level at university. But I didn't do that, so you get that bit, that little simple bit, and then often professors or postdocs or other students will say, but actually what's really interesting is this. And then you learn lots by asking those questions.
Yeah, definitely. It's something we all do as well. And I can use the example that I've just changed topic. Up till now, I've always been working on CMB stuff, dark matter stuff. Now I'm working on gravitational waves and phase transitions. And pretty much every meeting, there's a new word that I don't understand and a new concept. And I'm thinking, like, everyone else in the room knows what this is. But you still need to ask those questions because else, you're not going to understand it. So asking questions is never a bad thing. As long as you're actually asking. No, I'm not going to go off on a rant about that now. But yeah, it's always good to ask questions. You mentioned about different singing leading to different droplets, and David Howden is asking, what's the most disease-spreading form of singing? If you have an answer.
I'm afraid I don't know. I mean, I could take an educated guess, but no, I will try and find out, and I'll let you know, Deanna, and you can maybe share it in the future. I'll ask the people working on the singing and talking project. But
yeah, I think that would be very interesting to know. Like, put a ranking of how much they produce droplets based on how much you're singing. I see people from Reddit are trying to figure out where we're from. Good luck trying to figure out my accent because my accent is all over the place. I am actually from the south of the UK. I was born in Exeter. I grew up in Spain. I lived in Germany for 5 years and in Belgium, now in Finland. My accent is all over the place. British people tell me I sound German, so good luck figuring that out. But you are from the south, right?
Yeah, I'm from the south of England, yeah. I think I would say my accent doesn't sound like where I was born, but it just sounds like generic south, I would say.
Yeah, they got your accent right. So people here on Reddit were trying to figure out and said that I'm northern. It's like, no, I'm very much not north. I'm just, yeah, good luck with that. Comment from David here. It's always good to ask questions as long as you don't proceed it with this is more a comment than a question. Yes, definitely agree there. There's always somebody at the conferences doing that or at seminars.
Yeah, can I go back to the question of different types of singing?
Yeah, that's a really cool question.
So like I say, I don't know which genre of music produces the most droplets, but I do remember that in the just general speaking study they were doing of how aerosols and droplets are spread when people just talk, that there was a difference between, like, I don't want to say normal people, but like regular people who don't sing as a profession and professional singers, I think produced, I think it was more droplets when they talked, just because they've been training their vocal cords or their throat to be good at, enunciating and projecting. And so there was a difference between like professional singers and non-professional singers, which I think is an
But
interesting
when
difference.
speaking, not when singing.
Yeah, yeah, just when speaking as well.
That's really cool. I guess it does make a lot of sense, just something I'd never thought about.
Yeah, like, that's exactly how I felt when someone told me. I was like, I
Yeah,
never thought about it,
that's
but that makes
nice.
perfect sense.
So Paul is asking more questions about the method that you're doing and how you're doing the droplets. So do you analyze time stop photos, such as watching the spread of droplets from moment to moment?
Not yet. Well, we've tried, basically. We at the moment mostly study, someone or something coughs in a room, and we just take the end point of the droplets in that room, and then we have, like, we know they started in this person's mouth, they've ended up on the floor, and we can kind of predict the trajectory they took to get there. But to get sort of time, like, basically you want a video of it, and you need incredibly high resolution cameras to do that, and those are possible for us to get hold of, but difficult to. And then it's difficult to film. Then you run into issues of things like how much is in focus during the video, because you need a lot of light, and it's hard to then do it with the UV lights we have. So we really want to, basically, but we need a better camera, or we need a good camera for a long time in order to perfect it. But we would love to. Yeah, it's a great question.
That is nice. It's cool to think about these things as well. A slightly off-topic question coming in from YouTube, but I guess we can answer it. What happens to the electromagnetic wave once it leaves past the radio range? I'm actually wondering now, because we have the idea that as waves register through the universe, they get gradually stretched. We normally only think about going down as far as radio wave. What's after that?
I think it's just radio. I think it's just radio until nothing. As far as I don't think there's a name for. You just end up with, I think you'd call them extreme radio waves, which are, waves that are stretched or produced with, incredibly long or incredibly short frequencies. Like you can have peaks that are kilometers apart, and I think they're just extreme radio waves.
Yeah, I think at that point it's just like radio.
Yeah,
At some point
and
we,
then
we stop giving it a name. But that is very much not a silly question. It's one that, we're both thinking about now. It's definitely
yeah,
not a silly
I
question.
they would I guess they would be super hard to detect, though, because you'd need something sensitive that can look for long enough to pick up such. Yeah, it's a great question. I don't think it's a silly question at all.
Yeah, it's very interesting to think about, actually.
But if you have a wavelength longer than your detector, I guess it's hard to actually detect much. So you'd need an interferometer or something, I guess.
Yeah, you'd need something very big to detect that.
Absolutely.
So, we've talked a lot about droplets, and I know you told me that you're working on another project as well. And I think I could spend hours asking you questions about the droplets and how everything moves, but I want to hear about the other project you mentioned to me as well before joining, because that one also sounds cool. So, do you want to tell us about that as well?
Yeah, sure. This is much more in the early stages of me being involved, at least. But it's basically, we want to be able to take X-rays of fractured bones and diagnose them using a machine learning algorithm. So we want to teach an algorithm to find broken bones and just do it automatically without needing a doctor. Obviously, there are ethical concerns of how this could be used and at what point you should trust something like that over a doctor, which is a whole interesting debate that maybe isn't for today. But we're basically just trying to teach an algorithm to take in an X-ray, find a fracture, and tell us how bad it is. We would love to be able to do that. And machine learning right now is a very hot topic in cosmology. You can teach machines to do all sorts of things, like classify galaxies, tell you what kind of galaxy they are, classify their spectrum, talk about what sort of elements are in that galaxy. And we're basically using those really pure techniques and applying them to things like X-rays as well, which is super cool. And again, requires talking to a lot of medical doctors who talk a different language, but it's a super interesting challenge.
So I'm wondering here, what like, what's the advantage of using machine learning? So you save the doctor time, but like, what's the real advantage of using machine learning over an actual doctor for this?
Yeah, so the primary motivation is to save time and money. Often I think you have, if you have a very subtle fracture that still might need to be treated but is hard to see, then often it gets passed around many consultants and they spend a long time looking at it and trying to work out what's going on. And that costs a lot of time and money in the NHS. So they'd love to be able to streamline that process. So some machine can say, there's a fracture here, look closely right here, and you will see it, and then you can work out how to treat it. But also, the idea is really, really powerful in the sense that you can send it to places that don't have qualified, what's the word? Orthopedic
X-ray
consultants,
doctors.
X-ray,
Yes.
orthopedic people that deal with bones or specialists in X-rays. So, for example, third world countries or disaster areas where you might need to treat broken bones but don't have an expert, you could feed it into the same sort of system and at least have some idea of what's broken or what's fractured and treat it at least to begin with until you can get someone to look at it as well.
That does sound extremely useful. And I think if it works, it would be very nice, and as you say, it could help in a lot of cases. But then it comes back to the question. I'm always very slightly skeptical of machine learning personally, because it feels like there's a lot of potential for it to give you wrong results. Of course, there's a lot of good things being done with machine learning. How would you know you could trust the results?
Yeah, that is one of the things we're dealing with at the moment. But I don't know, to some extent, I kind of think it just needs to be better than a human, and then it's worth doing it. Then it's worth understanding it. But I don't know. Yeah, I think what you'd basically have to do is you'd have to train your algorithm for a long time, and then you'd have to use it alongside qualified doctors for a long time and make sure they're making the same or similar decisions all the time before you would ever use it on its own.
Yeah. And as Paul is just pointing out, there's also a lot of potential for people to give you wrong results. That is very true. There
Yeah,
is always
that's
human
exactly what I
error.
mean. Like it's
Yeah,
how I feel about self-driving cars. They don't have to be perfect, they just have to be better than people, and then they're worth it.
exactly. Yeah, because humans are very much not perfect drivers.
Yeah, but you're right. You need a lot of X-rays to input that you know exactly where the fracture is and stuff, and that's not a trivial thing to get hold of.
Yeah, yeah, definitely. I can imagine that the training sample that you need for this is going to be really big.
Yeah, and
This
then
seems. Sorry, go ahead.
I was just going to say we then have the interesting discussion of whether we try and teach the algorithm to diagnose in the same way that the doctors do. Like they told us how they, look at different bones and look at the angles of things, and that's how they often diagnose fractures and breaks. And then we have the question, which I think is interesting, and we haven't figured out the answer to, of whether we should deliberately try and teach it to diagnose in that way, or whether we just give it the data and the labels and say, you tell us how you're going to diagnose that, and we'll see if it's the same at the end.
Yeah, it's very interesting because machine learning does offer the option of moving away from the way doctors do these studies. So it's
Yeah.
definitely a big question. The thing I was going to say is it sounds like it's going to be a very long project. Like it's not something that you're going to be able to do in a year or 2 years.
No, I don't think so. I think we can make reasonable progress, but even if we got it working tomorrow, there'd be such a long testing process, and like you say, making sure it is giving accurate results that it would be a very long project. I think if it goes well, even if it goes well, I guess I should say.
I think it will be very, very interesting, though. There's a lot of potential. And there was a comment just now by someone saying that all this talk is making you depressed about your own mortality because of all the cool things we're doing now. But, the future is interesting, but so is now. Now is when we're setting the foundation for all of these things to happen. Now is when we're moving things. So, the future's cool, but honestly, so is the present. I mean, pandemic, wars, and all of that aside, and climate crisis aside, we are at a very, very interesting point in humanity. And, the future is bright, but so is the present. And I think it's cool to think about all of the things that we're setting the groundwork for now so that future generations can profit from. I do want to go back to something right at the beginning. You said you're on this innovation postdoc. And usually postdocs are short term, and it's always a bad question to ask in academia of like, what next? Do you imagine yourself staying in these cross-disciplinary projects and seeing how far you can take these really cool topics? Or do you somewhat miss the pure cosmology that you were doing during your PhD?
Oh, I hope my supervisors don't see this now.
No pressure to answer. Definitely no
No, no,
pressure
no.
to answer.
I'm happy. I'm happy to. I think at the moment I want to stay in this innovation field because I think these sort of projects are kind of the perfect thing to have short-term people on, but also I think you need someone there long-term to see the overall trajectory of the project. And I'm trying to convince everyone that that person should be me on these projects.
Definitely.
Because I think it's very easy to do something for a little bit, get some sort of result, and then move on, and then it kind of just gets left there with not achieving much. But I think maybe it's just because I'm involved, but I think these projects are worth carrying on for 4 years, and I'm hoping I can be that person.
Yeah, I mean, it definitely sounds like the projects, there's still a lot to be done, and there's a lot of interesting results and a lot of interesting questions to be asked. So I fully support that you should be the person doing this for many years. It
Could I get that in
definitely.
writing to send to some people?
Yeah, I'll just write that down. Like, based on, I am completely qualified to make these comments.
Definitely.
So we are getting close to 1 hour, and do usually try to keep the streams to 1 hour, though we often go overtime. So we have some people joining from your YouTube channel, but of course there's a lot of people joining from Haps, from Twitter, from my places. So do you want to just advertise your YouTube channel and like what you do in science outreach to my audience in case they want to go follow, which they all should go and follow your YouTube channel.
Sure, yeah. So my current target is to make one video every week about either a cosmology topic or a cosmology news story. So the last couple were about James Webb because it had this very cool image release and I wanted to talk about it. But yeah, I try and make them relatively accessible. I mean, I try my best, but sometimes I'm sure I fail as ever. But yeah, on YouTube it's just Chris Patterson. Just search my name. It's spelt funny, I think, but maybe I don't know if I can type it in the chat or something later.
Yeah, we can drop the link in the chat. Only people on Haps will see it, but we can drop it here for the people on
Sure.
Haps.
Cool. Yeah, and I try and talk about what I think is interesting or what's happening in the news. So Webb or I guess other space missions that are happening this year. I'll talk about as well. But then I also just cover topics that I think are cool, like gravitational waves, black holes, inflation a lot. Yeah. Yeah, I think that covers it.
And you've also done videos about how to go to conferences and how to get the best out of conferences. I think those were some of your earlier videos as well.
Yeah, I actually made a couple of those in Aachen when I was at Cosmo. So yeah, I started my YouTube channel just to sort of vlog going to conferences with no intention of it being a serious thing I commit to, just for fun, because I enjoyed traveling to these things and I wanted to have some sort of record of it. So they were really just for myself. But I enjoy making videos, so now I'm really trying to commit to one video a week, talking about cool science and making what I think are cool videos. I'm sure I'll look back in a couple of years and think I could be better, but I'm trying.
You should never rewatch your old stuff. Like I've watched some of my live streams from 5-6 years ago. It's like, oh, this is definitely work in progress.
Yeah, I think someone said to me recently that they saw the video I made in Aachen about like tips for attending a conference. It was the kind of idea of it. And this was obviously pre-pandemic, and they said, you just look so carefree and green, and now the world is so different back from how it was then.
Now you need to do another one of 5 tips for online conferences.
Yeah, it would just be how to make a good cup of tea and sit in your own office.
Yeah, how not to get Zoom fatigue.
Yeah, exactly.
Yeah, but so anyone following on my channels, make sure you go follow Chris on YouTube. Anyone following on Chris's YouTube, follow Cup of Cosmology as well if you liked what you saw today, because we do this every week. Not Chris and me, but I'm here every week. Sometimes with people, sometimes alone, just chatting about the universe. David, thank you very much for putting the link to cupofcosmology.com on all the platforms. I do appreciate it. It's easy to find. It's cupofcosmology.com. If you Google Cup of Cosmology, you find me. You can find the show. So before we wrap up, Chris, is there anything else you want to talk about? Any other projects? Anything else you feel you have to discuss before we wrap up? We can go over time. It's not a problem.
Oh, that's a really difficult question. I wish I'd thought about this in advance. I can't think of anything. I've talked about my pet projects of droplets and machine learning. We talked about inflation. We even talked about Webb, which I'm really excited about at the moment. No, unless there's other questions, then I'm happy to stay as long and answer as much as I can.
And we showed the CMB image twice today, so
Is that above average or is that about right?
that's about normal.
Okay.
Yeah, it needs to appear at least once per stream. I actually gave a talk about gravitational waves last week, and I still managed to slip in 2 CMB images.
Oh man, I'm really interested in gravitational waves at the moment. I think the detectors
It's
are super cool.
such a cool topic. The fact that I'm now partially involved in the LISA mission, like I'm working on stuff related to the LISA mission, and just thinking that we're going to have this space-based detector of gravitational waves is so incredible.
Oh, I'm super jealous because I think Lisa is going to be the coolest thing in the world. Well,
It's definitely, I think, the future. It's the hot topic to work on these days.
yeah, it's so mind-bogglingly cool, I think.
Yeah, yeah. I've had a few people from my group join recently, and it's basically just saying gravitational waves are so cool for the entire
They
hour.
really are.
And
They're
they
so
are. They're
cool.
such a cool topic. So thank you, David, for boosting Reddit. We do lose the Reddit connection exactly 1 hour in, but it's been boosted, so we have a few extra minutes on Reddit. That's good. So, Chris, thank you very much for joining. It's been really cool to have you on talking about things we don't normally talk about here and moving away from pure cosmology. So it's been really nice to hear about these topics.
Thank you so much for having me. It's been so fun.
This was your first time live streaming doing something like this, right?
It was, yeah. So no
I would
pressure.
honestly say I don't think that comes across at all. You're extremely good at this, and you're definitely welcome back on the show anytime you want. So if you want to come back in the future and update us on droplets, we'd be very happy to have you back.
I would love to. Yeah, thank you.
Awesome. Okay, so thank you everyone for joining, whichever platform you were watching on. It's been great to have you all here, and we've had some really, really cool questions today. So thank you everyone for all the questions. I'll be online again next Sunday, same time as always, at 7 p.m. European time, 8 p.m. Helsinki time, and there's a time zone converter on couplecosmology.com to find it in your own time zone. Next weekend, I have a professor from my department joining. We are going to talk about a few things, including general relativity, I believe is what we settled on. So that should be fun. I hope to see you all next Sunday, and I hope in the meantime you all have a great evening and a great week. And huge thank you to you, Chris, for joining once again.
Thank you so much. Appreciate it.
Bye, everyone.
Bye.